Great, so we're going to do problem 57 in chapter 8. Let me just organize my screen here for a moment. There we go. All right, cool. So problem 57, in chapter 8, page 246, a 10 kilogram block is released from point A. So we have this track that is a portion of a circle that is frictionless. Then it gets into rough frictional ground over a flat section. Then there's a little bit more of a flat section. And then we have the beginning of a spring here up against a wall. And they've labeled certain points here, point A, point B, point C. So A is the beginning when the object's at rest. So we're going to have an object released from rest here. It's going to come down here, point B to point C, and then it's going to hit against the spring. They don't label this point, but we will label a point D, which is when it comes to rest, right? So the problem kind of already picks for us the important points. So in our process, that's one of our steps. It kind of does that step for you. So let's go through our process. Step 1, draw a diagram. There's a diagram. Step 2, we want to label where our potential energies are equal to 0. So I have two potential energies I care about here. I have gravitational potential energy, and we'll say that that's at the ground here. We have spring potential energy. So we'll say US is equal to 0 there. So whenever the spring is at that US is equal to 0 line, there is no spring potential energy. Whenever any mass is at the UG is equal to 0 line, there is no gravitational potential energy. The third step would have been to write the important points. Got them, done. The fourth step is to write our knowns. We want to label our points before we label our knowns because we might know certain things at certain points in time. So we know the mass is 10 kilograms. That's not specific to a point. We know the length between B and C. So this length here, that's going to be a displacement between B and C of 6, or the magnitude of 6 meters. There we go. The block travels down the spring. We know that the spring constant is 2250 newtons per meter. And we know that point D here, where it comes to rest, the x position with respect to the US line, if we'll make to the right positive there, is equal to a positive 0.3 meters. Okay, and we're asked to find the coefficient of friction. We're actually also told the y position at point A is 3 meters, and we know that the object's at rest here. We know that the object is at rest here at position D as well. All right, cool. So those are the things that we know. Next, we want to talk about total energy statements. I like to do that. So I know that at position A, the total energy here is just UGA. At position B, the total energy has just become kinetic energy at B. C, the energy is still kinetic energy, right, because it's just moving along there. And at D, I've got that US, or the spring potential energy. Okay, cool. Next is to create links. Well, I know between A and B, there's no non-conservative forces doing work. There is a non-conservative force. The normal force acts here, but it's not doing work because the normal force here is everywhere perpendicular to the displacement. So that means I can say that the energy at point A is equal to the energy at point B because the work done by non-conservative forces between those is 0. I could also say that the energy at C is equal to the energy at D because the work done by non-conservative forces between those 2 points is equal to 0 as well. I've just got the spring force acting, which is conservative. Normal force is acting, doesn't do work because it's perpendicular. Gravity is acting, doesn't do work. It's both conservative and perpendicular, so no big deal. It's between B and C that we have an interesting situation because there's friction. So there is non-conservative work being done. So the work done by non-conservative forces between B and C is going to be equal to the final energy in that interval C minus the initial energy in that interval B. Now, I don't really know anything about points B and C, nor do I care about them, because I have a relation between B and A and C and D where I know things about point A and point D. So then this becomes my guiding equation. The work non-conservative that I care about is just going to be the work done by the frictional force here. I mean, theoretically, I should say the work done by the normal force as well, even though that's going to zero out, is equal to, and instead of EC here, I'm going to put ED because I know something about ED, minus, instead of EB, I'm going to do EA. And from here, the problem is fairly trivial to solve, right? I know that that's going to go to 0 because theta n is equal to 90 degrees. The work done by friction is equal to the size of the frictional force. The displacement, or really the distance over which it goes, But the magnitude of the displacement here is the same thing as that distance. Cosine of theta k is equal to, I know that this is spring potential energy, so this is 1/2 kx at d squared minus, and I know this is gravitational potential energy, mgy at a. I pretty much know everything in here except for the frictional force, so let's solve for the frictional force. So the frictional force then is equal to, this is 6 meters, cosine, well, if I were to draw a free body diagram of the thing in this location, and I have to, because anytime you have a work problem, and this becomes a work problem, I need a free body diagram, but let's be careful, I need a free body diagram where I care about the work being done. If I cared about work being done here, I need a free body diagram for it on the slope, and that would actually be pretty terrible, because that slope is changing slope over time because it's a curve, okay? And there's Fk, so let's just have that so we can very clearly see the displacements to the right. Fk is to the left, cosine of 180 degrees is equal to 1/2 k, which is 2250 newtons per meter. Xd is 0.3 meters, quantity squared, minus the mass, which is 10 kg. G is 9.8 newtons per kilogram, and Ya is 3 meters. So now we're just going to put a bunch of things into our calculator. I'm just going to calculate these numbers. Now, normally in a problem, I would probably recommend you find all these individual numbers and write them down. It's actually not really that purposeful in this particular problem because we're only asked the one thing. There's no B part of the problem. But just as a good problem-solving idea, remember, if your problem has multiple parts, it's often a good idea to find little bits and pieces about the parts because that could come into play later. Okay, not that we really needed to do that here, but just was convenient with the, I don't really like this calculator all that much. Make sure I don't make any math errors. So Fk, or the magnitude of Fk then, this comes out negative, so that gets rid of our negative side, which is good because I don't want the magnitude of a force to come out to be negative. That would not really have a lot of meaning there. So I have the magnitude of that kinetic friction. So to find the coefficient of friction, I just now need to do a force problem because I have to do a sum of forces in the y direction is equal to MAY because I need the normal force in order to calculate the coefficient of kinetic friction here, right? Remember, you have to do a sum of forces in order to find out what the normal force is. You can't assert it. The value of the normal force is dependent upon a lot of different things in different situations. Always do an equation to do it, even though here this comes out to something that we know it's going to be mg, but you have to prove it. Look, it's not all that much work. Just suck it up and do it. So 10 kg times 9.8 newtons per kilogram, 98 newtons, right? Good process. And so therefore, I can just finish it off by saying Fk is equal to mu k times the magnitude of Fn. 98 newtons is mu sub k. I'm sorry, I put things in the wrong place. 32.125 newtons is equal to mu sub k times 98 newtons. And then I can just find us a final answer. Mu sub k is 0.3, we'll just call it 33. We'll round there. Okay, cool. And that is how you do problem 57. It is a good problem that brings into a lot of things. And mostly it's a really good problem because it helps us talk about process and how we tackle these problems very systematically, break them into smaller little problems, and then through our links, pulling them together to actually get to solution.